Welcome, trigonometry friends. Today we will do another variation on Johnson-Jackson proof that c squared equals a squared plus b squared, the Pythagorean theorem using trigonometry. Okay, preliminaries. We think we're not using the limiting process. These infinite number of similar triangles. Also, we have sine alpha is a over c is cosine beta, cosine alpha b over c sine beta. Then we have our double angle formula and our difference angle formula for cosine as well as sine, as well as cosine 2 alpha. And we plug in the ratio versions and this is what we get. We've done that previously. And we'll also need to use sine of 90 plus alpha. That's cosine alpha. So here is the basic setup. We say, using the law of sines, u is to sine of 2 alpha. U is to sine of 2 alpha. As c is to sine of beta minus alpha. C, sine of beta minus alpha. That's the law of sines. Rearranging and using the ratio versions from up here and simplifying, we get 2abc over b squared minus a squared. If need be, pause the video and crank through the math and verify. Okay, that's one. Using the law of sines. Then we use the law of sines again. And what we say is v is to sine of alpha as u is to sine of 90 plus alpha. Here's u and here's 90 plus alpha. This is 90 degrees and this is alpha. So this is another law of sines, but 90 plus alpha is cosine alpha. So the law of sines basically gives us this. V is to sine alpha is used to cosine alpha. Rearrange, plug in the ratio versions, and you get 2a squared c over b squared minus a squared. So now we have v. Once we have v, we can calculate h. H is v plus c. So you plug in the values, make sure that you're properly normalized in the denominator, and simplify, and you get c parentheses a squared plus b squared is over b squared minus a squared. That's h, this distance h. But from cosine of beta minus alpha, that's u over h, u adjacent over hypotenuse. And so rearranging, we get h as u over cosine beta minus alpha. Well, we know what u is, and we know cosine beta minus alpha. That's this one, 2ab over c squared. So you plug in all these ratio factors, simplify, and you get c parentheses c squared, the whole thing over b squared minus a squared. Now take a look. H, we set these equal. So these are equal, h. The denominators are equal. The c's, they cancel out. And what you are left with is c squared is equal to a squared plus b squared. That's the proof that we want. And there it is. And we did it, and earlier I said that we did it without using a limiting process. That's maybe partially true, but partially not true. Look at this. Yeah, we don't have to use this geometric series where you're basically computing an infinite number of infinitely smaller and smaller segments. We did that in previous videos. However, if you think about it, sine of x is still x minus x third over 3 factorial plus x fifth over 5 factorial minus x 7 over 7 factorial plus dot 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 ad infinitum. So we really have not eliminated a limiting process, but that's the nature of trigonometry. So anyways, let me know what you think. I'm Mary and Elena. Thank you.